My name is Frank, data science fellow at Sharpest Mind. And to help us with the talk today is Amit Paka, CTO of Fiddler AI. A little bit of bio about Amit before we start. As we said, Amit is the co-founder and CPO of a machine learning monitoring company that empowers companies to efficiently monitor and troubleshoot ML models with explainable AI. Prior to founding Fiddler, Amit led the shopping apps product team at Samsung and founded Parable, the creative photo network now part of the Samsung family. He also led PayPal's consumer in-store mobile payments, launching innovations like hardware beacon payments, and has developed successful startup products, particularly in online advertising, paid search, contextual, ad exchange, and display advertising. Amit has passions for actualizing new concepts, building great teams, and pushing the envelope. He aims to leverage these skills to help define how AI can be fair, ethical, and responsible. I just want to inform everyone that if you have any question, quickly put it in the chat, and I'll aggregate the questions and ask Amit at the end of the 30-minute section. So for the next 30 minutes, Amit, you have our attention. Thank you.
Sounds good. Thanks, Franklin. And it's good to be here talking about machine learning and finance. That is one of the biggest verticals where we are seeing a lot of application and a lot of demand for not just operationalizing machine learning from the training and deployment perspective, but also from the monitoring and explainability perspective. So today I'm going to focus on how, when you want to operationalize machine learning ops, how do you reduce the risk, especially in the context of finance, with machine learning monitoring and explainability specifically. And I'll walk through how that can accelerate your MLOps lifecycle. And so a little bit about Fiddler. Our mission, we were formed about 2.5 years back, and our mission is to build trust with AI, and that's the focus on which the entire team of currently 40 people based out of Palo Alto work with. And our solution is a model performance management product that you see on the right side. It's a new stack that sits on top of a modeling stack where you can have models across a variety of layers of kind of frameworks. And that sits on top of data which can reside in one or more locations. And this model performance management layer sits on top of both these layers, giving you broad visibility into what's happening with your model and why it's happening with your model. And so this model performance management product is powered by explainable AI. And today I'll walk through why when you want to get visibility for your machine learning models, why it's useful to have explainability powered by monitoring. Questions while we're going through the presentation. I'll try to stop once in a while through the presentation and kind of capture questions and answer it as best. If not, I'll wait till the end and we can review it then. So let's get started. So of course, we've got a whole conference on machine learning within finance. So that should tell you how important this newer technology is. Just to quantify the monetary numbers that have been assigned, McKinsey has analyzed about $1 trillion in value add of AI and analytics to global banking. And this is across a bunch of use cases and internal teams within finance. And this is including traditional AI as well as advanced AI. And there's also a report from IHS Markit that quantifies this at about $300 billion. So there's a lot of value to be gained from machine learning in kind of finance, and this is leading to rapid ML investments as financial companies, banks, fintechs, and so on want to gain a competitive advantage and kind of really grow the top line. And so we're seeing the likes of JP Morgan expanding their team, specifically doing AI within Silicon Valley. So what does it mean to use machine learning in finance? These are some of the key use cases that teams are adopting AI. The first one and the most common one is assessing risk. And assessing risk can broadly be applied to, let's say, credit decisioning. Now with the use of alternative data really opening up, that is opening up a lot more opportunities of providing credit to a whole new pool of customers who had never had access to it. And machine learning is being used to really accurately quantify the risk. The second one is fraud detection. In case of fraud detection, it's very important that you use as much data as possible to be able to accurately identify fraud. And so fraud detection, the usage of large amount of data and doing it efficiently, that is something that's being like really done by machine learning. And then I won't go through the rest of these use cases. There's, of course, anti-money laundering use cases, know your customer checks. A lot of financial institutions are using machine learning models for recommendations of products that they have to users. And of course, when there are questions from customers using bots and so on to answer these customers and provide them with the right level of service. All these use cases, if you notice, they have very high impact. And they can have a dramatic impact to the bottom line and the top line, driving up to like the value that we saw in the previous slides. So this is why a lot of companies are expanding their AI machine learning teams within finance, just to capture all the efficiencies in all these use cases. But the problem with machine learning is, as it moves from the pilot stage or from the innovation labs into the real world where it's operationalized, it has a lot of risks. And these are the risks that we'll quickly go through and then walk through solutions for the risks. The key thing about, and there's two unique things about machine learning models. Number one is they're trained on a fixed set of data that is representative of the data that you will see when the model makes a live decision. For example, if you want your model to make a loan decision, you're going to train it with representative loans that are good loans that are bad loans. And so when it's trained, the model learns these relationships from that data set. And it goes and predicts which new loans that it's not seen are good or bad. Now, the new loans that it sees that are good or bad have to be in representative data to what you train the model with. And if it's not, then the performance or the predictive power of this machine learning model really goes down. And so that's one of the key reasons that you need to monitor machine learning models. The second unique trait about machine learning models is they can be a black box. And when these machine learning models are trained on the training set, you run automated algorithms that find the best possible fit. It could be based on the constraints that you have. You might have constraints tied to accuracy. You might have some other constraints, but typically it's the algorithm that captures all the relationships, the best way to actually generalize those relationships, and in doing so, it's very hard to understand which relationships it has captured. And it's this complex artifact with all the weights of all the relationships. So when it makes a loan decision, it's very hard to understand why it made the loan decision. For example, which of the relationships in the training set did the machine learning model absorb to make that new prediction. So these machine learning models are increasingly a black box. And so those are the two key traits that make machine learning models unique and warrant a new way to monitor them. So when machine learning models fail, the first thing that happens is the predictive power goes down. So the model can decay over time. And so you want to make sure that you're staying on top of real-time performance. Then the next thing is when you don't have a sense of assessing how the real-time performance is, you look at data shifting into the model. So you train the data with a certain distribution. You train the model with a certain distribution of data. However, when you deploy the model, your assumed reality of the world might shift, where the model is seeing new kinds of data, and so that might impact performance. Thirdly, typically, when a model is making live predictions or even batch predictions, it goes through, it kind of takes in live data, and this data can have a lot of integrity issues because there can be rapidly moving versions of data, there can be data pipelines, and so the data that your model sees, it can have slight errors, and that can impact your metrics over time. Fourthly, your model, when it's trained and when it's deployed, it can add and amplify risk, and this creates regulatory and brand risk, and you want to stay on top of it before your model fails. And lastly, transparency, and we'll speak more about this. Because these models are machine learning, these machine learning models are black boxes, it's very hard to reason about why they're making decisions and why they have a certain behavior or explaining that behavior. Let's actually deep dive into this last one. So most models are a black box today. So really, as you go from the lightweight models, let's say a logistic regression, all the way to like machine learning models, which are, let's say, random forests, they get more complicated, and then going on to deep learning models. As you build your models with these complicated algorithms, they of course give you higher accuracy, help you absorb a lot more relationships, but they also become a black box. And because of that, there's no visibility into how the model is doing. It's very hard to monitor for drift and potential bias. And of course, it's very hard to explain why the model is making a certain decision. And this is not just a data scientist problem. This impacts all the stakeholders that you see on the right that are involved with this machine learning model in some way, whether you are a business user trying to launch a model and making sure that you understand what you're launching. If you're customer support, how do you answer questions? If you're IT operations, how do you monitor the model? And of course, if you're a data scientist, ensuring that you know how the model works. And especially in the case of finance, if you're working with an auditor or a regulator, how do you ensure that you're communicating the behavior of this model and that the decisions are fair and comply with regulations? And on the note of regulations, historically there have been like all the existing regulations that make sure you don't discriminate against a certain protected class, and of course there's specific regulations which were released around the turn of the last crash. These are XR 11.7 and the actual OCC bulletin, and they provide guidelines on how you can ensure that you know everything about the model, where the data is coming, how you're training it, that you're about to launch, and that you monitor these models. These actual guidelines were built for the previous analytical models, but they're now also applicable to the machine learning models. And there's also new proposed regulation coming out. And so a recent example of this is the trustworthy AI regulation that was proposed. It's still in the proposal phase by the EU. And the goal of this regulation, you can see to the right, is to ensure that customers have trust in AI. And so, especially in the context of the EU regulation, it classifies the risk of each AI system from from use cases that are banned to use cases that are high risk to use cases that are low risk. But for the high risk ones, this includes credit decisioning. They mandate visibility in the form of monitoring a model and in the form of the ability to explain why the model is making decisions. And so below you see a bunch of news events that happen, and these are just in the last couple of years. When you have models that have not been validated well, and so like most recently there was the famous case of Apple Card issue, where husband and wife in the same household were getting dramatically different credit card limits, even with the same income and so on. So this is just to point that if you don't stay on top of ensuring that your models work well, it can be a PR. It can bring a PR and a brand issue. And with all these problems, the machine learning teams on the ground, they don't have the necessary tooling, and so they are essentially flying blind. And so if you look at just the challenges that we've seen in the news around model transparency, where there was a case of TikTok where there wasn't enough transparency in how the algorithms work, and that was raised as like a national priority issue. And then like looking at, of course, coronavirus impact last year when consumer behavior shifted. For teams that didn't have visibility into their model, they were caught off guard because their models were making faulty decisions or lower performance decisions. And of course, looking at the Apple Card event again and going more into regulated use cases where if you don't assess your models for bias, if you don't ensure your models are compliant, you can run into a lot of fines or PR issues. So we looked at the challenges and we looked at what can happen when things go wrong. So what is the right way of ensuring your machine learning models are operating the way you want them to and meeting the guidelines? So the right solution is it's like an APM for AI and machine learning. So APM is a term from the DevOps world. So it's called Application Performance Management. And within DevOps, when you run software, you get full visibility into how that software is working, from the application layer to the infrastructure layer. So you have solutions like Datadog and AppDynamics that gives teams full visibility into how the applications are working. And so there's nothing like this today for AI and machine learning teams. And which is why there's a need for a model performance management, which is analogous to APM. We call it MPM, that helps teams explain what's going on with their models, monitor those models, and analyze when things are going wrong, like really to your models. And so you get visibility into what is happening into your models and why it is happening. Now let's actually dig into this a little deeper. So how does MPM help illuminate this black box to give you visibility? So the way it does that is it plugs into your inference pipeline. So your model is making live decisions. And so you want to make sure that all the predictions that your model is making is looped back into this MPM system. You also want to make sure that the training data that your model is using, or a sample of the training data, which can be a representative baseline, goes into this machine learning model like MPM system. And when that happens, you get monitoring through with the help of your predictions coming in, using a sample of your training as a baseline. You can do validation in the context of your training data. And then combined, you can analyze the model deeply on why is the model doing what it's doing, whether you're trying to validate it or whether you're trying to ensure that it's working the right way in a real-time life context, whether you're trying to debug or root cause something. And so this is where it sits in your life cycle. And I'll share a little bit more about the broader machine learning life cycle with training and kind of deployment in like a few slides down. So how do you catch operational issues after you've deployed a machine learning model? Let's actually dig into that. What happens when you deploy a machine learning models? So the first way that you can catch if your model performance, let's say a machine learning model is actually deployed. How do you ensure that you can monitor well so that you can be alert going awry? So the first way is you catch performance issues with labels. So your model is making predictions and you get input whether it is the right prediction, and that is the label. And so with this label, you can assess the how accurate was your model's prediction. So like, let's say, for example, you have a real-time model. Let's say you're at Instacart and you're using a machine learning model to recommend a product to a user to add to cart. If the user adds the product to cart, you have a positive label that the model made a right decision. If the user does not add to cart, then the model made the wrong decision. So using these real-time decisions, these labels can also be lagging. Using these real-time labels, you can calculate how accurate your model is, and then you can set alerts if the model's accuracy or whatever metric drops, then you'll be notified. And you can have tens of these models. So once you set up alerts, then you'll be notified, as long as you have labels coming in. And you can use metrics like let's say MSE if you have a regression model, log loss, and so on. And so there's a bunch of metrics that teams typically model, like really monitor. And so the problem with this system is you need labels to come in, whether in the real time or in the lagging context. And so not a lot of teams get to do it with this first approach using labels. So then they lean towards a second approach of monitoring performance, and they do it with drift. Now, if you don't have labels coming in, how do you assess that your model's performance might be going down or decaying? And so the theory behind using drift is when you train your data, when you train the model, you're using representative data of a certain distribution. And so you expect production data to come close to that distribution of data that you trained it with. And so when the production data changes from your training data, that might be a leading indicator that something is going wrong with your model. For example, we saw how in the start of the pandemic, shopping behavior changed. People, instead of searching for something else, now started searching for hand sanitizer. And so models were not recommending hand sanitizer because they were not retrained with this new data. And so data shifted. And so when you use drift and drift metrics, it helps capture how is this data changing in the context of what you train the model with. And so you can use this to inform. So here what you're seeing on the far right is the dark blue line shows how the drift goes up, right? So as the drift kind of doubles, you can set an alert, and you could use metrics like let's say KR divergence and so on. So there's like a bunch of metrics you can use to quantify drift. And as long as you set an alert, you can be notified of the model that's going awry, and it can help guide your retraining, or maybe for you to really root cause why that might be happening. The third thing that can happen to your model is is the data going into the model. It can run into data errors, and there are three kinds of data errors that a model can see. You can have missing values. Now, some teams might impute the values in case they are missing, and if that is the case, that will cause a data drift. But if that is not the case, it will show up as like a model. So if there's a make a prediction, right? It'll just not be the most accurate prediction. You can also have a range or a type mismatch, right? For example, if you have, let's say, 50 states in the US, and for some reason there's a 51st entry that your model sees. So that would be an example of a range mismatch. So if you have visibility into all the inputs going into your model and what is the right constraint, you can capture all these data issues like right away, because they have a tendency of kind of eating away at your model performance slowly over time. And kind of lastly, even if you've assessed your model for bias at the validation stage, as the data changes, when your model goes live, it's possible that there could be operational bias introduced. So you want to ensure that you're monitoring like a cohort for certain model metrics that you're using for like bias metrics, or at the global level, to make sure that there is no new operational bias being introduced. So these are the four key ways that your model can run into operational issues. But let's say you find the operational issue. What do you do with this operational issue? Typically, like in a data scientist, like they see a ticket, and then they have to go and root cause, like what's causing that drift, what's causing the performance decline, right? And that can be very tedious because you have to recreate like the same version of the model with the same version of the data, replay all the predictions, and then really deep dive. And that could take days or even weeks. So here's where explainability kind of is really useful. And I'll go into a little bit of detail about explainability, but let me talk about how explainability can be used. So you can explain a single model prediction or inference, and that will tell you how does each input into the model impact that output, that model output, right? And it could be, for example, in this case of a loan, if the loan is, let's say, denied, it will tell you that, hey, because the debt to income was that much, that contributed, let's say, 30% to the loan denial. So that's the first way of how you use explainability in the context of one prediction. The second way is you can explain a cohort itself. Like, let's say you were going beyond just a single loan. Let's say you were trying to explain all the loans from the state of California. How are they different? How is your model treating them differently? So how do the inputs impact each other and the output? What are the features that are important in that cohort? And finally, explaining a model globally, explaining all loans in the case of your training set or in the case of your live data. What are the features that are important and how are the features interacting with each other? So these are the three granularities of where you can use explainability. Let's go through each one of these. So when you explain a prediction, there's multiple ways and kind of techniques that you can use to explain it. And here's a few top lists. One is Shapley based kind of techniques, and the way they work is they change the inputs in like a combinatorial way, and they look at the change in the output, and then they do an aggregation and tell you what actual input contributed the most to the output. So it does this attribution, and so it does it in a very in like a combinatorial way. And in case of gradients, you've got gradient-based, techniques that are applied only to differentiable models where you can get, gradients. And of course, there's a simple way of using ablations where you just take out the input and then you see the output. And so what you see on the right is how would this show up to an end user, which is a data scientist or like a machine learning engineer. So if you're trying to explain, let's say, a probability of risk, in this case, it's a pretty high risk of 0.235 for a loan. So this is a loan decisioning. And so you can see debt to income of 34.81 had a 20% impact on this predicted risk. So now you have a sense of why is the model making a decision? What of the inputs is contributing to this high risk? And similarly, if you had a text model, right? In this case, it's using a gradient-based explanation technique, and it's trying to do a sentiment analysis, and it's giving a positive sentiment. So you can attribute the positive sentiment to which of the words are the ones that are contributing positively. Now you might think explanations might not be the best way and the most accurate way. Recently, there have been remarks by the Fed, specifically Governor Bernard, who highlighted the importance of explanation in the absence of anything or nothing today to really help understand stakeholders how a model is making decisions. And she goes into detail into why explanations need to be contextual depending on who it's being offered to, whether it's a technical person or whether it's the consumer of the explanation, let's say the actual end user who's applying for a loan. So the Fed is really thinking about how do you use explainability in and kind of providing guidelines to like the rest of the financial community. You can explain a segment in like a similar way. In this case, what you're seeing is I'm doing a bank churn example where I'm trying to predict churn of customers specifically in the state of California. And so using feature importances, partial dependence plots, or model metrics. So here I can explain why is the model doing what it's doing for this group of customers from like California. So you can see here, I'm looking at a feature impact plot. I can see in the dark blue line why age is the most, what is the impact of age in this group of customers from like California versus the rest of the customers. So the light blue line is the rest of the customers. So now you can compare and contrast. And you can also see these kind of partial dependence plots of all the customers in California. You can do feature correlations. You can do slice evaluations. So this gives you a good understanding of how would you explain a segment or a model. And you can put all this explanation into a model report. This can also be shared to, let's say, if you have a compliance team or a model risk management team, you can put all these charts to help the actual compliance team really understand how the model is behaving in the context of certain cohorts. And kind of, so now speaking about how do monitoring and explainability kind of come together? So here's an example of how they come together. We spoke about how when there is a drift, you can use a metric to identify when your data is shifting. And in this case, you can see from the dark blue line that the drift was constant and then the drift spiked. So now you can use explainability to really root cause what is causing it. So in this case, you can click on this time range where you're seeing the blip. And below, using explainability, let's say you've got hundreds of model inputs. You can figure out that which of the inputs, in this case, number of products, is causing the most impact to this drift, which is happening in the model. And then you can deep dive and see, oh, number of products in this case is actually causing the most impact to this drift. And you can see that what your model sees in the production, it sees a lot of customers that have 3 to 4 number of products versus what you trained it. And then you can deep dive using explainability and say, in the state of Hawaii, you're seeing a lot of customers who have 3 to 4 products versus what you trained the model with. So in this case, what happened is the state of Hawaii eased restrictions on a certain type of business loan. And that resulted in a lot more customers having 3 and 4 really number of products. And that skewed the model. So tying the context of the business with what's going on in the model is what you could do to really help root cause the problem. And so explainability here really helps to drill down on top of visibility that monitoring provides. So I'll start to recap and kind of share a little bit more about how machine learning, how model performance management can work across the machine learning lifecycle. So in the training, in like the training set, in like the training step, you can log all the training and test data sets, and you can check for bias and the feature quality. In the validation step, you can ingest the model and explain. You can do the cohort-based kind of really analysis. You can see why are the slices or these cohorts having lower performance. You can compare with the champion challenger cohort. When you deploy, you can record model traffic and the metadata. If you have champion challenger, you can actually compare that. And once you start monitoring, you can observe how the performance is decaying. You can check for drift, you can check for outliers, and then really compare if you have champion challenger, if your new model is actually working well, and then you might want to swap it out. And finally, if let's say your actual champion model is seeing drift, you want to analyze what's going wrong. If it could be due to data issues, it could be due to some other changes in the reality that the model is seeing, and then you can root cause what's causing a performance issue and feed that back into the training set. So the thing with machine learning models is you don't just create one model, you create versions of models, and there's this constant iteration of like converging to the right level of like accuracy and deviating, and then converging and deviating. So having a sense of what is causing the problem and feeding that back into your training set and retraining, this is where MPM really can help, and it sits on top of your life cycle and gives you broad visibility into how your model performance is doing. This is already being used by some of the large banks, and here's how a top 5 bank in the US uses model performance management. They use it in the model validation step and the model monitoring step, and there's all these other 10 steps that go into validating and deploying a model and retiring a model. But these 2 steps are where model performance management really kick in. And so I'll stop right there. Thank you so much for listening in. I'll take questions now.
Thanks for a great presentation, Amit. Thank you so much.
Thanks, Kushal.
Guys, please put your questions in chat.
Cool. It looks like there are very many questions. In case you do have any questions, feel free to drop me a note. I forgot to include my email. It's amit@fiddler.ai. I'm happy to answer any questions related to monitoring explainability. This is probably a very dense kind of quick walkthrough, and so feel free if like to request for these slides. I'm happy to share and maybe send it through maybe Kushal as well. Hope to see everybody else on the rest of the sessions.
All right. Thank you so much, Amit. I feel your presentation was really good, and see you around.
Thanks,
Thank you so much.
Vishal.
Thank you so
Thanks,
much.
Vishal. Cool.
All
Thanks,
right. Have a good
everyone.
day.
Bye.
Bye bye.